Imagine a box. The famous one. Inside, a cat, a vial of poison, a single radioactive atom. You know the dark logic. If the atom decays, the cat is gone. If it holds, the cat is fine. The laws of quantum mechanics, tested for 100 years, insist that until you look, the atom is not one or the other. It is a perfect, mathematical superposition of both decayed and not decayed. Which means the cat is suspended in a state of impossible contradiction. Both alive and dead. But let's get personal. Forget the cat. The choice to open the box is yours. Your hand is on the latch. 1 hour has passed. When, in this entire chain of events, does the universe actually commit? When does it flip the coin? Is it the instant the atom splits? The moment the hammer strikes the vial? Or only in that final, heart-stopping second you lift the lid and face the consequence? That shimmering, razor-thin line between might be and is the single greatest and most profound mystery in all of science. Tonight, we are not adding more confusion, more hype. We are auditing that boundary. We are drawing the most honest, detailed map of the measurement problem and what it means for the very fabric of your reality. First, before we can audit reality, we need to understand the tools the auditors use. We need to look at the universe's own blueprints. The most fundamental concept is the quantum state, but it's not what you think. It's not a tiny marble or a spinning top. It's a description of pure potentiality. The proper term is a probability amplitude. Think of a weather forecast. It might give you a 70% chance of rain. That's classical probability, a simple number representing our ignorance. The probability amplitude is deeper. It's like having access to the entire atmospheric pressure system itself, the swirling, underlying wave of high and low pressure that generates the 70% chance. It's the reality before the fact. This amplitude is like a complex ripple on a hidden, silent pond. Where the ripple is high, the probability is strong. Where it's low, it's weak. And here's the kicker that separates it from anything in our daily lives. These amplitudes are not just numbers, they're more like sound waves. They can interfere. Two ripples can meet and create a taller wave, constructive interference. Or, crucially, they can meet and cancel each other out completely, creating a dead zone where a particle will never be found. That is the true magic of the quantum world. Possibilities can subtract. So how does this wave of possibilities move through time? There's a law for that, an ironclad rule at the heart of quantum theory: unitary evolution. Forget the intimidating name. Think of it as a perfect, cosmic choreographer. It guides the ripple on the pond with flawless mathematical precision. This evolution is perfectly smooth, perfectly continuous, and most importantly, perfectly lossless and reversible. In the pure math of quantum mechanics, no information is ever destroyed. The total amount of possibility always remains the same, it just gets rearranged. It's like an immaculate, timeless dance where every step is perfectly defined by the step before it. You can, in theory, run the film backwards and recover the past perfectly. This is what allows the system to be in a superposition, to be riding many different melodic lines at once. An electron isn't just here or there. Its wave of possibility is literally in both places simultaneously, and the different parts of that wave interfere with each other. This is not a metaphor. It is the mathematical reality. But we don't live in a blurry wave. We live in a world of concrete facts. A click on a detector. A line on a test. So how do we get from that ghostly wave of potential to a hard, definite outcome? This is the job of the Born rule, and it's one of the deepest mysteries we have. The rule itself is brutally simple. To calculate the probability of finding the particle at a specific spot, you take the height of its probability amplitude there, the intensity of that ripple, and you square it. That number is the chance you'll find it there if you look. For a century, this rule has been the unbreakable bridge between the strange quantum math and the real-world results of every experiment ever conducted. It has never, ever been wrong. The terrifying part? Nobody knows where it comes from. Why squared? Why not cubed, or something else? The universe simply decrees it so. It's an ad hoc rule that just happens to work perfectly. And finally, what is this mysterious act of looking? What is a measurement? For decades, we were told of an observer who magically collapses the wave. That was always a placeholder for a deeper understanding. Real life is messier and more physical. The modern, honest way to describe a measurement is with a mathematical tool called a POVM, a positive operator valued measure. I know it sounds awful. But the concept is simple. Imagine you're a detective trying to identify a suspect's car color from a blurry, black and white security camera photo taken at night. You can't say it's blue. You say, there's a 60% chance it's dark blue or black, a 30% chance it's gray, and a 10% chance it's a dark red. A POVM is the rigorous, mathematical version of that. A real detector isn't a perfect on-off switch. It's a fuzzy lens. It interacts with the quantum system and gives a probabilistic, often imperfect answer. It's not a philosophical act performed by a consciousness. It's a physical interaction between one complex system, the detector, and another. So if the entire universe, at its base, is governed by this perfectly smooth, reversible dance of ghostly waves, why does the world I experience seem so brutally decisive and irreversible? Why does an egg, once scrambled, never unscramble? Where is all the quantum weirdness? The first and most important piece of the puzzle is a process called decoherence. If you learn one word today, let it be this one. Quantum systems are shy. They maintain their beautiful superposition only when they are perfectly isolated. The moment a quantum system touches its environment, and the environment is everything, the air molecules in this room, the photons from the sun, the faint vibrations of the earth, it becomes entangled with it. Entanglement is a deep topic, but for our purposes, it's like this. It's like taking two threads of the purest, most vibrant color, the quantum system and its environment, and weaving them together so tightly that you can no longer tell where one begins and the other ends. Their fates are now inextricably linked. Their quantum story becomes one vast, combined story. What is the practical consequence of this? This entanglement frantically broadcasts the quantum system's secret, its delicate superposition, out into the environment. The interference pattern doesn't technically vanish. Instead, it gets smeared out, diluted, and shared among trillions upon trillions of particles in the environment. Let's refine our analogy. Imagine a single, masterfully crafted bell ringing in a silent, vast cathedral. You can hear its pure, resonant tone, a beautiful superposition of its fundamental note and all its overtones. That is our pristine quantum system. Now take that same bell and ring it in the middle of a colossal, roaring factory floor. The sound of the bell, its physical vibrations, is still there, spreading out according to the laws of physics. But can you distinguish its pure tone from the chaotic cacophony of 1,000 machines grinding and stamping? Absolutely not. It's been utterly drowned out. That drowning out is decoherence. Reversing it would require every machine in the factory to play its noise backwards, in perfect time, to reconverge on the bell and cancel out. It is practically, and therefore for all intents and purposes, physically impossible. But right here is the absolute core of the measurement problem. Listen carefully. Decoherence explains why we don't see macroscopic superpositions. It explains why a cat isn't both alive and dead to us. It explains why the world appears classical. But it does not, by itself, select a single winner. The roaring factory noise drowns out the bell's unique tone, but it does not magically cause the bell to become unrung. Decoherence leaves you with a set of stable, classical alternatives, a live cat, dead cat, and it explains why they can no longer interfere with each other. But it says nothing about why we experience only one of them. It turns a quantum mystery into a classical-looking menu of options, but it doesn't place the order. So what does? Enter the second major piece of the modern picture, quantum Darwinism. If decoherence is the process of information uncontrollably leaking into the environment, quantum Darwinism describes how that information survives and what it becomes. This is a profound idea. It suggests the environment is not just a passive, noisy dumpster for quantum information. It's an active, colossal witness. A cosmic publishing house. Let's go back to our system, say, a single dust particle. Some of its properties, like its delicate quantum phase, are incredibly fragile. Information about its phase gets smeared into the environment as a completely unintelligible mess, like a whispered secret that gets distorted into gibberish after one telling. It doesn't survive. But other properties are robust. Its position, for example. The particle's location is a pointer state. Why? Because every single photon that bounces off it, every air molecule that nudges it, carries away information about its position. That specific piece of information gets copied, and copied, and copied billions of times per second, into countless independent fragments of the environment. The environment becomes saturated with redundant records of the particle's location. This is survival of the fittest, but for information. Only the most robust, copiable information gets to survive the harsh reality of the environment. And this gives us a physical, non-mystical definition of objectivity. What is an objective fact? In this view, a fact is a piece of information that has been so massively and redundantly copied into the public record of the environment that many different observers can independently access a small fraction of those copies and all come to the same conclusion, without ever having to disturb the original system. You and I can both agree that a tree is standing in the field because we are both intercepting different photons that have all bounced off that same tree, all carrying the same redundant story. Tree is here. We don't need to ask the tree. We just need to consult the public record it leaves in the light. Facts, then, are not magical things created by consciousness. Facts are the triumphant survivors of a ruthless selection process. They are the public truths that have earned their existence by being copied into oblivion. Now, this beautiful story would be worthless if it didn't match what we see in the lab. And it does, perfectly. The experimental evidence is the bedrock beneath these ideas. It all starts with the double-slit experiment, the most beautiful and unsettling experiment ever devised. You fire particles, electrons, photons, even large molecules, one at a time, at a barrier with 2 slits. If you don't watch which slit they go through, they build up an interference pattern on the screen behind. This is the universe screaming at you. Each particle went through both slits at once, as a wave of possibility. But the moment you install a detector, any detector at all, no matter how gentle, to find out which slit each particle used, the interference pattern is obliterated. Instantly. It behaves like a simple marble. Why? Not because you observed it with your mind, but because your detector had to interact with it. It had to leave a physical record. It entangled with the particle, and that single bit of witch path information leaking into the environment is enough to destroy the superposition. The particle no longer has a secret to keep. And then, we get to the quantum eraser, which takes the weirdness to a whole new level. In these astonishing experiments, we first measure the witch path information, destroying the interference. But then, and this is the key, after the particle has already passed the slits and is on its way to the final screen, we use a clever quantum trick to erase the information our detector collected. We scramble the record, making it fundamentally unreadable. And what happens is nothing short of miraculous. When we look at the data corresponding to the erased information, the interference pattern comes back from the dead. This proves beyond any doubt that this is not about human knowledge. It's about physical information. The universe doesn't care if you know the path. It only cares if a record of that path exists somewhere. It's a cosmic game of bookkeeping. No surviving record, you get interference. A surviving record, you don't. We have relentlessly tested this boundary. Loophole-free Bell tests have become exquisitely precise, showing that the correlations between entangled particles are stranger than any story of local, pre-existing properties can explain. It forces a choice: either the world is non-local, things can be connected faster than light, just not for signaling, or reality doesn't exist until it's measured. Both are staggering conclusions. And we're pushing the scale. Scientists have seen quantum interference with molecules made of up to 25,000 atoms. These are objects so large they have their own temperature and color. Today, in labs around the world, physicists are in a heroic race to do something once thought impossible: to put a macroscopic object, like a tiny vibrating mirror or a levitated glass nanoparticle, into a superposition of being in 2 places at once. The goal is to see where the rules finally break. Does reality itself have a resolution limit? We are right on the verge of finding out. And yet, even with decoherence and Darwinism explaining the appearance of a classical world, the cliff remains. We are left with a menu of classical outcomes, but no rule for why we experience just one. The hard data of our experiments takes us this far, and no further. The final step is a choice of interpretation. And each story you can tell has a profound, reality-altering cost. First, there's the oldest and most pragmatic, the Copenhagen interpretation. In its modern, stripped-down form, it's the engineer's creed: shut up and calculate. It declares that the purpose of quantum mechanics is not to describe reality with a capital R, but to predict the probabilities of experimental outcomes. The quantum state isn't a picture of the world, it's a tool. The collapse of the wave function isn't a physical process, it's the moment an experimenter updates their knowledge. It puts a black box around the moment of measurement, and says, our job is to predict what comes out, not to speculate about what happens inside. Its virtue is intellectual discipline. Its metaphysical cost? It leaves the world beyond our measurements as a profound, unknowable mystery. It refuses to tell us a story about what the world is like when we are not looking at it. For those who crave a story, there is the most extravagant and mathematically pure, the many worlds interpretation. MWI takes unitary evolution, that perfect cosmic dance, as the only law there is. It declares that the wave function never, ever collapses. So what happens when you open the cat's box? Simple and terrifying: the world splits. Decoherence doesn't just suppress interference, it cleaves the universe into non-communicating branches. In one branch, a version of you finds a live cat, feels relief, and continues their life in a universe where the atom didn't decay. In another, parallel branch, an equally real version of you finds a dead cat, feels sorrow, and continues on in a universe where it did. Every quantum measurement, happening constantly everywhere, is branching the universe into a near infinity of parallel realities. There is no special you are a pattern, and that pattern is duplicated across the branches. Facts are branch relative. The virtue? It requires no new physics, it is the most literal reading of the math. The cost? A metaphysical baggage of unimaginable proportions. A cosmos filled with ghost copies of yourself, living out every single possible outcome. If that's too much to swallow, perhaps you prefer Bohmian mechanics, or a pilot wave theory. This interpretation says, what if reality is more straightforward, just with a hidden layer? It posits that particles, like electrons, are real particles. They have definite, actual positions at all times. They are not blurry waves. But their motion is infallibly guided by a hidden pilot wave, which is the standard quantum wave function. So the wave explores all possible paths, interferes with itself, and creates a complex landscape of currents and eddies. The real particle is like a tiny, mindless surfer, being pushed and pulled along one single trajectory by these invisible quantum currents. So you get the wave behavior, because the wave guides the particle, but you get definite outcomes, because the particle was always in one place. The wave never collapses. The fact is just the path the surfer took. The virtue? It feels more intuitive, more classical. The cost? The pilot wave must be non-local. It has to instantly connect the entire universe, guiding every particle based on the state of every other particle, violating the spirit, if not the letter, of relativity. Then come the revolutionaries who say, maybe the math is just wrong. These are the objective collapse models. They propose that unitary evolution is only an approximation. There is a second, undiscovered physical law, a law of collapse. Superpositions, they suggest, are inherently unstable. They have a natural half-life. A tiny system like an electron can hold its superposition for a very long time. But for a massive system, like a cat, which is made of trillions of particles, this instability compounds catastrophically. The probability of a random, spontaneous collapse into a single state becomes overwhelming, happening almost instantaneously. There is no observer needed, the universe collapses itself. Gravity is a leading suspect for the cause. The virtue here is immense, it solves the measurement problem cleanly, giving us one world with real, absolute facts. The cost? It means modifying quantum mechanics, our most successful scientific theory ever. And so far, every experiment designed to find evidence of these spontaneous collapses has come up empty. Finally, we have the most philosophically radical shift, cubism and relational quantum mechanics. These views turn the entire camera around. They argue that a quantum state does not describe the universe out there. It describes an agent's, a user's, state of belief about the universe. My quantum state is my personal user interface for reality. It's my betting book on what I should expect from my next interaction with the world. A fact or a measurement is not a universal event. It is a transaction. It's an update to my personal ledger when I interact with the system. You have your ledger, I have mine. There is no absolute, God's eye view of reality. The universe is a network of interactions, and facts are created locally at the interface of those interactions. When we agree on a fact, it is because our transactions have correlated. Its virtue? It dissolves many paradoxes by making reality perspectival. The cost? It may dissolve objective reality itself, leading to a kind of scientific solipsism where the universe is fundamentally a story told from a single point of view. We push these stories to their breaking points with paradoxes. Wigner's friend is the ultimate clash of perspectives. Let's walk through it slowly. Your friend Alice is in a perfectly sealed lab. Inside, she measures a quantum coin and sees heads. She writes it in her notebook. From Alice's perspective, a definite, irreversible fact has been created. The superposition is gone. But from your perspective, Wigner, standing outside, you have not interacted with the lab. So according to your rulebook, pure unitary evolution, the entire lab, including Alice and her notebook, is now a single vast quantum system in a superposition of Alice sees heads and Alice sees tails. So who is correct? Has a fact been created or not? This isn't just a riddle. It forces the question, are facts absolute, or are they relative to an observer's perspective? Many worlds says the world branched when Alice looked. Relational quantum mechanics says both you and Alice are correct from your own points of view. Copenhagen tells you the question is meaningless until you open the lab. This paradox lays the problem bare. And we have the hard constraints of mathematics. Bell's theorem is a mathematical proof that the world simply cannot be both local and realistic in the way Einstein hoped. It cannot be made of things with pre-existing properties that are only connected by influences that travel at or below the speed of light. Decades of increasingly precise experiments have confirmed the quantum predictions. Something classical has to give. The Kachin-Specker theorem adds another layer of weirdness: contextuality. It shows you cannot assign pre-existing values to all the properties of a quantum system simultaneously. The answer to what is the spin on this axis can depend on what other axes you decide to measure at the same time. The question you ask influences the reality you get. A fact doesn't exist waiting to be read, it is created in the act of measurement. So is it all just philosophical debate? Absolutely not. As we discussed, objective collapse models make testable predictions. If random collapses happen, they should produce a tiny, constant background noise, a faint heating of the universe. This has motivated a generation of physicists to perform some of the most delicate experiments ever conceived. They take a nanoparticle of glass, levitate it with lasers in a near-perfect vacuum, and cool it to within a whisper of absolute zero to eliminate all normal vibrations. Then they watch it with agonizing precision. Is there a tiny, inexplicable jitter? Is there a random heating they can't account for? So far, nothing. The silence from these experiments is deafening. With every no result, the space for objective collapse models to hide and shrinks, and the case for the untarnished, unitary-only stories grows stronger. So, after this deep and honest audit, where have we landed? Can we walk away with a working definition of a fact without having to pledge allegiance to any one metaphysical camp? I think we can. It is this. A decision in nature is not a moment in time, but a process. It is the emergence of stable, classical information that has been so redundantly recorded in the surrounding environment that many independent agents can discover it, and all come to the same agreement about it. Facts are not ethereal sparks ignited by a conscious gaze. Facts are physical footprints. They are the durable, public records left behind by a quantum system's interaction with the world. They are the triumph of information that was fit enough to survive. And how you interpret those records is your final choice. In many worlds, the records are branch relative. Every possible set of public records exists in its own universe. In relational views, the records are agent relative. A fact is just a completed entry in my book about my interactions. In objective collapse, the records are absolute. The universe itself acts as the ultimate accountant, ensuring only one ledger is ever kept. Each story carries a heavy price: a proliferation of universes, the dissolution of objective reality, or the modification of our most cherished physical law. Let's bring this all the way home, to the human scale. When did your last big idea become real? Was it when you felt that first flash of inspiration? Of course not. It was a private superposition of possibilities. It became real when you wrote the business plan, when you spoke the marriage proposal, when you sent the email, when you coded the first line. It became real when your private possibility entangled with the public environment, leaving a durable record, on paper, in someone else's memory, on a server that others could then access. Our reality is built on the moments we transform our internal quantum states into classical, shared records. In the most profound way, the universe and our own lives are governed by the same principle. Reality begins where the durable record is written. So where does reality decide? It decides at the messy, physical interface where fragile possibilities are overwhelmed by their environment, and where their secrets are copied into the public domain. The beautiful math of quantum mechanics doesn't shout a single interpretation at us. It whispers the constraints. It maps the boundaries of our knowledge and forces us to confront the profound nature of what it means for something to be real. As you leave this audit, notice that moment in your own life today. The moment one of your private possibilities becomes a public fact. What does that boundary feel like to you? Of all the grand stories we've audited, the pragmatism of Copenhagen, the vastness of many worlds, the hidden guidance of Bohm, the random jolts of collapse, the personal ledger of cubism, which one resonates most with you? Let me know in the comments. There is no wrong answer, only a different story to tell about our shared universe. We conduct these hype-free, deep dive audits of reality every single day. If you believe that clarity is a worthy pursuit, do yourself a service. Hit that subscribe button and ring the bell to join this ongoing investigation. The algorithm has analyzed the universal wave function and selected another audit just for you. It's on the end screen now. Click it, and our conversation will continue.